So what you can write here is dl equals to f upon pi Young's modulus r square, and this is L upon b minus a into dr. Now this is also integrable. So fl by this L is not a variable. Unfortunately, the symbols are such. Let's call dl dash just to avoid confusion. So fl by pi b minus a y and dr by r square. Now this is integrable easily. So this will go from a to b. The r will go from a to b. So the deformation and this integration is 1 upon a square minus 1 by b square. Sorry, 1 upon a minus 1 by b minus 1 by r. So this will be like this. And you can see this answer is exactly what we are looking for.
Yes.
So b minus a will cancel out. Okay. So this is how you can solve from basic. In the hanging example, it's even more tougher. So that you can discuss in the tutorial.
Yes, sir.
Yeah. So we are done with the Young's modulus. So we can go to the other one. So other one is bulk modulus. And the symbol is B. So bulk modulus we define as normal stress which means the force must be perpendicular to the surface upon volumetric strain. So the strain must be volumetric. So you can write like sigma n upon epsilon v. And bulk modulus is defined for a three-dimensional medium, which may be solid, liquid, or gas. And here, because the dimension is not very much specific, whether it's one dimensional or two or three. So when we have a real world objects, then bulk modulus is the best way to proceed. Okay. So like for gases, we cannot define Young's modulus. For liquid, we cannot define the Young's modulus. For solid, we can define Young's modulus. But bulk is defined for all three cases, solid, liquid, and gases. So for solid body, the Young's modulus and the bulk modulus will have some relationship. For liquid and gas, because we cannot define, so we have only bulk modulus. So when to think of bulk modulus? Whenever we have objects in which uh, there is no finite, dimension which we can deal individually. Let's say if I cannot deal with the x dimensional changes and y dimensional changes and z dimensional changes independently, so I will prefer going back to the three-dimensional changes, and that's how we relate the bulk modulus. So bulk modulus is the way to deal with three-dimensional medium of any arbitrary shape. Even the shape doesn't matter. So generally for gas and liquid, we prefer bulk modulus, but bulk modulus can also be applied for solids. So it's not like we can apply only for liquid and gases. So B is defined for all types of medium. So how we write this? Generally for liquids, we have seen that the way of writing bulk modulus is if we have some and if we have some object. Okay. So if it is in a liquid, then the force due to liquid will act at a right angle to the surface everywhere. So this is the force acting on the body from all directions. And therefore, the bulk modulus we can define as sorry. So you can see the bulk modulus will be normal stress, and normal stress is basically in case of liquid, the normal stress we define as the excess pressure that we create. So when you dip the object into the liquid, the pressure will grow. So what additional pressure you create, the additional pressure will be the equivalent of normal stress. So the word stress we replace by the pressure in case of liquid and gas both, and we divide by the volumetrication which we have defined as minus delta V by V, because the volume will shrink because of the pressure. Volume is going to decrease, so the negative sign is for the purpose that uh, it will be a negative number. Delta V is negative number, and therefore minus will make it positive. So this is how we define, because the modulus of elasticity cannot be a negative number, so it must be a positive number. Okay, so this is the way of defining. This you can also write as minus V delta P by delta V, but we prefer writing in the differential form. In differential form, the way we write is you can see it's a differentiation of pressure with respect to volume. multiplied by the actual volume in without deformation. So when you multiply volume with the pressure gradient with respect to volume, what you get is called uh, bulk modulus. So this is the definition that we use to derive various formula. So now in case of gas, so bulk modulus is also defined for gases. So in case of gas, the bulk modulus depends on the thermodynamic process. In case of gases, and I will stick to the ideal gases. So in case of gases, bulk modulus B depends upon thermodynamic process okay. So there are two very famous bulk modulus for two famous process, and there are some generalized process also. So we'll start with something very simple like isobaric. So isobaric means you do not change the pressure. So delta P itself is 0. So there is no question of bulk modulus. So for isobaric, the bulk modulus will only call 0. If you say isochoric, which means delta V is 0,
Infinity.
so the B becomes infinity. So that's why these two are not defined actually, because it's meaningless. So in a realistic condition, we only define for the isothermal and adiabatic. So the two which are famous are these two only. So we'll define for isothermal bulk modulus. So what is isothermal bulk modulus? So for that you need to have differentiation of pressure with volume, and to differentiate P with V, first you need to have the relationship, right? So we know that for isothermal process, PV equals to constant, correct?
Yes, sir.
So you can differentiate both sides. So PdV plus VdP equals to 0. This is one way of differentiation. Or the other way is write the partial derivative. So how we write the partial derivative? dP by P plus the fractional sum is 0. You can just write like this. And this is the easier way. You just write the fraction of each term which are multiplied. So we have two terms multiplied. So we write two terms fraction, and the multiplication becomes summation. So that's the interesting part. And whenever we have a product of number, you can take the log both sides to make it summation. Okay, so that is also possible. So you can do the third method is taking log both sides. So ln p plus ln v equals to constant, because ln constant is constant. And now if you differentiate, you will get 1 by p dp and 1 by v dp. So this is how we write. So be it any method, when you should be comfortable with this method, you take the log and then differentiate. That is always easy mentally. So what you will get eventually?
So can you show the previous page?
Done.
So the minus V delta P by delta V is the universally true for Poisson.
Pardon? Yeah, it is always true. So in case delta V becomes positive, the delta P will be negative, not naturally. So it will remain V will be positive.
Done.
It is like that if I decrease the pressure, it will in a way blow up. Okay, but that is not the case for solid bodies. So when you go to orbit, let's say those astronauts who go to the space station, and when they live there for about 1 year, the bone density decreases, if you know this fact.
Yes.
And that is why when they come to Earth, they cannot walk right away. So they need to be first acclimatize with the Earth gravity, and then they actually start living normal life. So it takes time for them, their body to again go back to the Earth gravitational field, and that's the biggest issue with them. So what they do is they keep on doing exercises even in the uh, spacecraft so that they can keep their bone density intact. Okay, there are very various things about life. So dP by P plus dV by V equals to 0. So we got the volumetric extent. So I can have dP by P. This is exactly minus volumetric extent, right? But anyway, so volumetric extent we can also write for this process as a dP by P, right? That's interesting. Anyway, and dP upon EV is how much? That's exactly the definition of bulk modulus. Anyway, so you can write from here separately. So dP by P equals to minus dV by V. So V dP by dV equals to P, which means the pressure of the gas itself is the bulk modulus. If the gas undergoes the isothermal process. So B isothermal is equals to the P, but this P represents the equilibrium pressure of gas. And this is very, very important for the next chapter, like sound chapter, because the velocity of sound is in a gas is adiabatic process, but Newton thought this as isothermal process. And so we have two different formula for velocity of sound. One is called Newton's formula, other is called the Laplace formula. Anyway, so coming go to the next adiabatic bulk modulus. So adiabatic bulk modulus is basically if the process is adiabatic. So PV power gamma is constant if you know the adiabatic process.
Yes, sir.
This is called called the sorry, guiding equation. And again, it's very easy to differentiate. You can take log both side and then differentiate. Or the best way is just add the fraction. And while adding the fraction, the power gets multiplied because that's come from the log only. So this is the easy way to differentiate. If you don't know, then just learn this method. And then from here, if you write the minus V dP by dV, you get gamma times P. So this is the definition of bulk modulus, and we can see the bulk modulus for adiabatic process turns out to be gamma multiplied by pressure. So we can say that the B adiabatic is always more than B isothermal. And because you have already studied the thermodynamics, so what I can say that for a polytropic process, which is a generalized process, so what is polytropic process? Anyone knows?
PV equals to constant.
Hmm?
It's a PVM, V to the power M is equals to constant.
No, I'm asking what is polytropic process. I'm not asking the equation. What do you mean by polytropic process? When we say a process as polytropic,
So like general process.
so if I write P equals to, or maybe P square equals to V minus AV minus alpha V minus beta by V square, is it polytropic process? Is it polytropic process? Tell me. It's a general process, some random process. Can we say this as polytropic?
No.
So you said any process is polytropic. So what is the definition of polytropic process? When we say a process is polytropic and when we don't say. So all thermodynamic processes are not polytropic. So a process in which the molar heat capacity of a gas remains constant is called polytropic. Process in which molar specific heat capacity actually molar heat capacity molar, yes, remains constant is called polytropic process. So whatever you study in thermodynamics are polytropic process. So adiabatic is a polytropic, isothermal is a polytropic, everything is polytropic. So all process which you study are polytropic. Okay. So the C must be constant. And where C come from? C come from the dq by n dt. So this term must be constant. And if it is so, then we say, what do we say? Polytropic process. Understood?
Yes, sir.
And you can prove it also, like because as I said, this dq by n dt is constant. And we know dq equals to du plus dw, which you know from first law of thermodynamics. So you can also write as du plus dw by dt equals to constant, because n is a mole, so that's also constant. You can use these two equations, and dq du you can write as n cv dt and p dv upon dt equals to constant, like some constant. And you can see that if you write further, so ncv plus p dv by dt is again a constant, and this you need to simplify further. So you can use the ideal gas equation P equals to nRT, and therefore P you can replace by nRT by V, right? So using this three equation, you can again get NCV plus nRT uh, yeah, nRT by V actually, dV by dt equals to again constant. And then you have to just rearrange everything. So NCV itself is some value. So what you get is NR upon gamma minus 1, you know, CV value. This is NR, and that's very interesting. It's dV by V upon dt by t. is a constant. And then you can take n as constant, so 1 plus 1 by upon gamma is 1 plus dv by v upon dt by t is again constant. So it's like a rearranging, and then eventually you'll get like some t power some constant minus 1 equals to constant. So this is how we prove, and from here you can go back to get p power x equals to constant. Or there are multiple ways to derive. Okay, I can substitute and do the. I just took a different path, but we can derive it. It's not difficult. So that is how we prove that it's a that's a formula for a polytropic process. So the whole idea is simple. Unless the molar heat capacity is not constant, we cannot say polytropic. And polytropic is process for, I mean, of process in which the C remains constant. Because if C becomes variable, then we say just a process. We don't say polytropic. So the example which I gave, those are not polytropic. Okay. Anyway, so for polytropic process, the bulk modulus will be very simple. It will be the polytropic exponent x into p. You can say, and x is called polytropic exponent, just like gamma is called adiabatic exponent. So the PV power, the power is called exponent. Okay, that is how we say it. And that's why when you derive the formula for the C, you will get the answer as R upon. So because X is constant, so C is always constant. So this is the formula of C for any polytropic process. So if I put X equals to gamma, it will become 0. And that is exactly the C for the adiabatic process. So you can choose a process and you can substitute X. So if I say P by V equals to constant, this is as good as PV minus 1 equals to constant, and therefore X turns out to be minus 1. So C of this process will be how much? And so it turns out to be R upon. So this is the C of this process, which is again some new constant. So let's say if I give you it's a monatomic gas. So for monatomic, it will become interesting. So C becomes 2R. Okay. So for different process, the bulk modulus will vary, and this is very important from the point of view of sound chapter. In sound chapter, we have to derive the bulk modulus for the two processes that we just mentioned. So there I will not be deriving. I will be using this result. Okay.
Sir, I want to see the last.
Okay. Just this page.
So that was R minus gamma minus R by gamma minus 1.
Yeah, R upon gamma minus 1 minus R upon x minus 1.
Yes.
So this we derive from the first law of thermodynamics only, from here.
Yes, sir.
So all derivation we derive in thermodynamics from the first law and the ideal gas equation, and uh, various property of process will give you the answer. And it is good to write in differential form so that you can integrate or differentiate as and when required. When you solve the thermodynamics in physics, the differential form will help you. Okay, so the bulk modulus is done. So what next? All right. So we can find the volume changes. Okay. Do this question. So let me derive the relation. So as I said, bulk modulus and Young's modulus are related to each other. Young's modulus talks about one particular direction or dimension. Bulk talks about all dimensions taken together. So if we have a object, let's say if you have a block, and I'll keep a block as a cubical block so that the area remains same everywhere. Maybe I can do the okay. So this is a cube, and it is kept in the water. So from all directions, some extra force will act. No, no, this is something difficult you can understand. Okay. So one is from behind. So everywhere, and let's say this extra pressure delta P, I just name as P because that's easy for. And you can think the length as L. So imagine only one dimension along the x-axis. Say this is x-axis. Imagine this direction. So the pressure is trying to decrease the length, right? So the pressure will decrease the length. What about the other? The top pressure, what it is trying to do? So top pressure will try to expand it, isn't it? So the x dimension is decreased by the right and left pressure, but at the same time it is also increased by the top and bottom and front and back pressure because of the lateral strain concept. So I want to know what is the actual change in the length. So from the definition of Young's modulus, what we know? From the definition of Young's modulus, we know that stress is Young's modulus into strain, longitudinal strain. And sorry, the strain we can also write as sigma by y, or you can say p by y. So this is the strain actually. The definition, the x is pressure. So here the pressure is the normal stress and the strain is the Young's modulus. So this is how we can define the strain. So I want to know the total change in length, and what you can see that the length that is going to change is equals to minus p by y because it is decreasing but the two sides will increase laterally. So you can see the lateral strain is what? Negative of the longitudinal strain. So other two pressure will try to increase it. So this is the part which you need to understand. Is this clear?
So that is +2 and then.
Pardon? Or two times, because the top and the bottom, this pressure will try to increase the length. But for this pressure, the increment is lateral, not longitudinal. So we use the Poisson ratio.
Yes, sir.
So the Poisson, so we know that the strain in this direction we know, and strain in this direction will be how much? Mu times this value. Mu times. So the strain in the direction of applied force is P by Y. So strain in the transverse direction is mu times that value.
Yes, sir. Understood.
And because we have two separate push trying to inflate the top and bottom and front and back, which I haven't shown the back on the red, behind the red actually. So the length will grow by this value. And the same you can write for the width also or height also, but I'm just taking a cube, that's easy for me. So the volume I can write as L cube, correct? So the dV by V we can write as 3 dl by. And so this you can write as -3 P by Y. You can see the volumetric strain we have this relation. So how we define the volumetric strain? Minus dV by V, which is equals to 3 P by Y 1 minus 2. So what is the definition of bulk modulus? So bulk modulus is defined as excess pressure upon volumetric strain, correct? And if you do so, what will you get the answer? You can see the B comes out to be Y upon 3 1 minus. This is the relation. So bulk modulus and the Young's modulus are related by the relation B equals to Y upon 3 into 1 minus 2 mu. Okay. So you just need to remember this. So this is easy to remember because you look at this number 3 1 2. 3 minus 1 is equal to 2, right?
So can you explain that dl by L is equal to minus of n?
So volume of a cube is how much?
So that dl by L is equal to minus P by Y.
Okay, this one. Okay.
Yeah.
So here one is the direct strain, which is the longitudinal, and this is the transverse strain.
Yeah. Okay, sir.
And this is longitudinal. So transverse will try to increase the length, not decrease, right?
Yes, sir.
You have to think of one dimension at once. Don't take all three together. Imagine that what will happen to the length if I apply pressure from the top and bottom? Will it increase or decrease?
Decrease.
Only take care of the transverse forces. What the transverse force will do? Will it increase or decrease?
High.
Sir, increase.
Yes. So only
Sir,
the
2 times
longitudinal.
because from both sides.
Yeah, because of two separate pair of pressure. You can see enough top and bottom.
Yes.
Look at this. This and this is one factor, and this is other factor. Understood?
Yes, sir.
That the two lateral factors, and there is only one longitudinal factor for each side, right? So only one factor is decreasing, but two factors are increasing. But the increment factor is because of the Poisson ratio. It is not exactly same. It's a 2 times of, I mean, the mu into the longitudinal strain. Understood? So this you need to realize. This is the part which is difficult. But even if you don't know the derivation, at least remember this well. Because this was asked in the JEE mains. So I have been teaching this since 2009, and JEE asked eventually in 2020. Okay. 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 So what else we have to do in bulk modulus? In bulk modulus, I mean, you need to find the volumetrication mostly, and things will be really simple. So they may ask you find the, let's say, let's take this question. If we have a sphere of radius some value r, and if you take the sphere and if you put it in the bottom of a lake, then definitely let's say the depth is some value h, and density of the liquid is rho. So the extra pressure that will develop here is how much? Rho
Rho
gh,
GH.
if you know the answer. So here the pressure is P atmospheric. Here the pressure is P atmospheric plus rho gh. So what is the extra value? Rho gh. So this is the additional value which you have developed, and so it will try to compress.
So like we have to always take the extra.
Yeah, we have to always take the extra value, not the value under which you are already present. Okay. So every, let's say if I'm the manufacturer of a ball bearing, and let's say I get a contract from the some submarine company to create the ball bearing for some purpose. So I know that the submarine is going to work under extreme pressure because it will be under the depth of the ocean, and therefore and let's say if we want to design the submarine itself, so the submarine must be designed in a way that it should be able to withstand the pressure that is developed because of the depth you go into. But the submarine is not manufactured inside the uh, water, right? What where we manufacture is in the factory. So when once you manufacture, the moment it will go inside the water, it will get compressed. So we have to think of or optimize the thickness of the submarine, which can withstand the maximum possible depth it will undergo. So let's say if it is designed to go up to 300 feet. So we just need to create the thickness which can tolerate the pressure up to 400 feet, because we always keep the margin. So if I have designed my submarine for which can withstand the pressure of 400 feet liquid pressure, then anyway it will be good with 300 or 200 or 100 or surface. So these things are very important. I mean, it looks something very simple, but it really matters. It really matters for the real world manufacturing. So now, okay, you will see this effect very closely. If you have seen the gas cylinder at home, have you seen the gas cylinder anyone?
Yes, sir.
Yes.
And if you look at the design of the cylinders are not designed by one complete closed iron shell. If you look closely, there are two half shell, which is welded in the middle. Have you seen that?
Yes, sir.
So the point where they weld together, that is the weakest point, because that is the welding point. So that's the weakest part of the cylinder. So because of, let's say, if a fire will catch inside the cylinder, then the pressure of the gas will expand, and because of the excess pressure developed beyond the limit of cylinder, it will detach from there. So they make sure that the debris will not be everywhere, rather it will be in one dimension. So because cylinders are kept horizontal, so the moment it will blast, it will try to go into two halves, one up and other down. Okay. So the danger is that if it happens, then it goes vertically up, and it will try to break the floor also if it is not good enough strength. So we always give the weak point in a material so that the breaking happens in certain way. If I do not give any breaking point, then it will just break from anywhere, and that is more dangerous, isn't it? So excess pressure is the issue of a blast. It is not the pressure. The pressure is already there. So everything is designed for certain pressure, but if fire catches, then the entire 14 liter will try to expand at once, and expansion of gas is adiabatic process, so it will create tremendous pressure which cannot be withstood by the iron shell. Okay. And if you want to prevent the fire, then you have to make the cinder thickness maybe 10 times more than that. Now, that will be very costly, right? We have to also think of budget or economy. Anyway, so P equals to P naught plus rho GH, and delta P is rho GH. So we know that the bulk modulus of the material, we can hardware it. Bulk modulus will be is extra pressure, right? Rho GH upon volumetrication. So I will just add sigma V. You can say sigma V turns out to be how much? And sigma V is basically dV by V minus. And for a sphere, because volume is 4 by 3 pi r cube, so dV by V can replace by 3 times dr by r. And therefore, you can write from 1 and 2 minus 3 dr by r equals to. So the fractional change in the radius or decrease in the radius is how much? So they may ask to find the percentage change in the radius. So So this kind of question will be asked. That how much radius will decrease? Now B is so high that this value will be a very small fraction. So in fact, you won't be able to see these changes. But in submarine, these changes are very much significant. And they know that if there is a bigger compression of the submarine, entire submarine, then the chance of breaking is also there. So it may crack, and that will be very dangerous. If it cracks, then it will sink only. There is no way out. So you will never go up. You will only sink. Anyway. So all this designing uses the concept of elasticity, and they go much beyond this simple calculation. They have very complex computational calculation before they design the shape and the length and the everything else. Anyway, next. So imagine I'm manufacturing some iron shell. And it is filled with some gas. And what is interesting is that the thickness of this shell, because that's very important. So it may be a cylindrical shell, it may be a spherical shell. So I'm taking the example of a spherical shell. Thickness is T and radius is R. And it is filled with gas. So we may have some inlet, I'm not showing that. So question is, if the breaking stress, if sigma B is the breaking stress, of the shell, what is the maximum pressure that we can develop? To find the maximum pressure of the gas above atmosphere, because the gas pressure will try to push it and the atmosphere will try to compress it, so that is balanced. So what is the extra pressure above atmospheric pressure? So at up to what pressure can fill this sphere without breaking it? And breaking stress is known to us. So how to do questions like this? So it is very difficult for beginners. So stress is the calculation of force acting per unit area on the cross section of a body. So you need to first draw the cross section of a body. And for any object, the best way to draw the cross section is by imagining the two equal parts. So I will draw the one half of the sphere for this purpose. And what you're looking is this part. Let me show you what you're looking right now.
The call from +91703911
So now okay, you can see the radius. So when you try to fill the gas will push the cylinder, right? And it will push the wall of the cylinder, and the pressure that we will create inside, the pressure P, or let's say delta P, must be pushing the cylinder like this, like this, like this, everywhere. It is pushing everywhere. So how to find the resultant force on the half, like say half sphere? So it is very easy. The net force will be equals to the excess pressure which you create into the projection area, which is equals to pi square, the base area. Because it is acting in all directions, so the net will be equals to the base area. So the shape really doesn't matter. What matters is the base area, and this is the force acting because of the gas. Now, if the gas is trying to push the half sphere towards the right, who is stopping? Who is preventing the half center? So it is opposed by the material itself. So the connection, as you can see, so it is acting everywhere, as you can see, right? This is the wall it is holding, right? It is pulling it to prevent from going towards right. So this is the force developed. Okay, you can name the force. And this force is what? This force is a distributed force. Okay. So how much is this force? So force is defined as the total force, if you write, is defined as is stress into area. What is the area? What is the area of this force? So it is the area of a thin circle, right? Thin, I mean, if you understand this, 2 pi r into t. On this area, the force is acting, right? Because it is acting only on the thickness part, right? And thickness part is very small, isn't it? This is the thickness part. This part it is acting, right? You have to imagine the internal structure of the sphere to solve this question. Do you realize this? Yes or no?
Yes, sir.
So now for balancing, so now the next part is just at the equilibrium. So for equilibrium, the stress into 2 pi RT must equals to delta P into pi R square. So delta P is 2 sigma naught thickness upon radius. This is the answer. It is clear? Okay. So if it is clear, then we can solve some question. Okay. So let me send the question.
So you can see the question which I have sent on group.
Yes, sir.
So solve question 1.291. A part. B part we have done, but you can also solve B part also. And take the breaking stress as sigma because that is not mentioned there. So sigma you have to assume on your own. That's it. So we have just solved the B part. You have to solve the A part. And don't use numbers, only solve in symbols. Okay? Don't solve using numbers.
Sir, we have to assume sigma here.
Yeah. Always assume sigma. Sigma as a breaking stress of material. So you are supposed to solve from the top to bottom, all question from top to bottom. So there are only 10 questions, right?
Yes, sir. Sir, answer is in terms of sigma.
Yes. Answer is in terms of sigma only. The same you will get for A part the same answer. I think B part the same answer. 2 sigma delta R by R for B part.
Yes, sir.
It's the same question actually. For A part, what is the answer for the cylinder? If it is cylindrical tube, then how you will draw the ABD? So you have to take the length of the tube as some value. Na? Take as L. Solve it. And we always take the projection length. So if you can draw the ABD, then you're done. Then it's very easy. So you have Europe book at available to you.
Yes, sir.
Yes, I'll just send the answer because in many cases, some variables you have to assume on your own. That will be known from the answer given. So let me send you the answer. Okay, anyway. So I think this is like a good question for you to do in tutorial. So I'll go to the next concept. You can practice in tutorial. Okay. So generally we assume the liquid as incompressible liquid, but every liquid will get compressed, and therefore we do have the bulk modulus of liquid, which is very high because they compress very less. So let's say bulk modulus for a liquid is B, and So let me read the question from SC Verma only. That is SC Verma question. So this is the question number. Yeah. Question number 13. 1-3. So we have to find the variation of pressure with depth. Yeah, I put a heading. Variation of density by depth. So generally we assume density as constant, right? So density is constant, of course, indeed is constant, but there is a slight variation because of the depth of the water, and that is because of the bulk modulus. So let's say the density of the water near the surface is rho naught. So the density at some depth will be a rho if you go h below. And now I'm interested in finding this rho value.
Am I audible to you?
Yes, sir.
Yes. Sir, why is the dpdv equal to 0?
Pardon?
So why is that dpdv is equal to 0?
Oh, d rho dv, no? D rho dv. This, no?
D rho d.
Because these are two differential terms. So these are very small, no? So compared to this,
हाँ,
this is it.
Sir,
Hmm.
so please will you explain this because your voice wasn't.
Okay, one second. So first of all, pressure we write as rho gh in a liquid, and then you can differentiate to get a pressure variation as a depth. You can say dp equals to rho g dh. Then we derive the relation between the volume change and the density change. So mass is a constant quantity. So let's say at a given depth, the density is rho, volume is v of an object. So if you go further below, the density may change to this value, volume may change to this value, but the mass of the object remains same, right? So by keeping the mass is constant, you can equate this to value, and solving this will get this answer. Is this particular?
Yes, sir.
Now we use the definition of bulk modulus, which is minus dp by dv by v, and the dp we can write as minus b into dv by v, and then substituting the value of dv by v as minus d rho by rho, we have this relation. So now when the height is 0, the density is rho naught. When the height is h and density is rho. And this will give you some answer. Minus 1 by rho, so 1 by so so 1 by rho not minus 1 by rho is gh by b, right? Yeah. So 1 by rho is how much? So yeah, this is correct. So you can take LCM. Okay, I think we should have taken like this. And generally rho not gh, it is very small compared to the bulk modulus itself. This is very small number. So we can use the binomial approximation to write like this. So for a small depth, if h is small, the bulk modulus will be much bigger than the term, and therefore you can use the binomial. So now you can solve the question number 13. Tell me the answer. Or is it the answer matches? Just tell me.
So are you getting the answer now?
One.
Yes, sir. Sir, I got the answer.
Good. So now we can go to the last topic, the last definition. Am I audible? Hopefully. Hello, hello, hello.
Yes.
The last topic was the modulus of rigidity. The symbol I will keep is eta. This symbol you must have seen. Just write n and stretch the right part more. So this is different from the remaining definition. So modulus of rigidity is defined as the tangential stress upon shear strain. So we use the tangential stress upon shear strain, and you must have seen this diagram.
So this is the force acting on this area. This is the theta. So the tensile stress constant is F upon A, or you can say tangential force upon area. And the shear strain that is theta, right? If you remember the definition. This is like
Yes, sir.
X, and this is, let's say, L. So X by L is the answer. So the tensile force we can also write as eta. Okay.
Yes, sir.
So all right.
Sir, I want to know the last.
So what I'll do, I'll just mention one more thing. A relation between eta and Young's modulus. It is also there. I will not give the proof. So the eta we write as Young's modulus divided by 2 times 1 plus 1. So something like this. Okay. So just remember the two definition. This relation and the relation that we have derived already. So we have Young's modulus, and then we have bulk modulus, which is we write as we have eta. So every modulus of elasticity for solid body we can always write or always express in terms of Young's modulus. So by eliminating the common variable like mu, we can obtain the relationship between y, b, and eta. So we have to have relation between Young's modulus and eta. So we can use the last two equations, and that's easy. So if I call it 1, so from 1 we can write as 1 minus 2 mu is y by 3, and 2 will give you 2 plus 2 mu is y by 8. Just we need to add this. So mu will cancel out. So it is 3 equals to So that is the relation 1 by y is 1 by 3 eta plus 1 by 9b. So this is the relationship. This was a JE 2020 or 21. I don't know. So the second thing is we can also determine the theoretical range of mu. So all modulus are positive numbers. So you can see that from the 1. Theoretically, mu must be less than 1 by 2. And 2 implies 1 plus mu is positive, which implies mu is more than minus 1. So there is a range of mu theoretically. This is the theoretical range. Possible, but practically we always keep from 0 to half. Okay. So the mu is not negative, but theoretically it could be negative. So these are the theoretical and practical range of Poisson ratio that they generally ask. And we are supposed to remember this. Okay.
So I want to see the last one. Done, sir.
Okay. The next is this is the last topic of this chapter, energy analysis. So whenever a body is deformed and if the deformation is recoverable, then it is similar to the concept of perfectly elastic collision. So if deformation is there and if it can be recovered 100%, we say it is elastic, perfectly elastic body. And because it is having the ability to recover completely, 100% recovery is possible, which means that the energy is not lost, rather it is stored as potential energy. So deformation, if recoverable, I mean, we prefer to say that this is storing energy as a potential, and you can take it back, you can recover it back. So every deformation actually represents some sort of potential energy. Okay, and recovery is like if it is in the elastic region, then it is also recovered back. So it will keep it for some time and it will give it back. If we have a permanent deformation, it means some microscopic potential has been changed permanently and the energy is lost there, so you cannot recover it. So in our syllabus, like when we are studying the elasticity, what we need to remember is that the elasticity and the elastic deformation are always stored as potential energy. So what we can write is as a concept that elastic deformation always gets stored as potential energy. Okay. So elastic deformation always is stored as potential. That is what we need to remember. So now how we define the potential energy? So there are two definitions of potential, but we'll in this chapter, in deformation chapter, in this chapter, we'll only take the first definition, and that says that the change in potential energy is always equals to negative of work done by system. And work done by system you can write as work done by the restoring force. And why this definition? Why not the other definition, which is says that delta U is equals to this is only true when the external force is not creating any other form of energy. So let's say it is not creating kinetic energy, it is not creating heat energy and so on. So we are not sure about this part. That's why we are not using. So in this chapter, the only definition that we should use for calculating potential is work done by restoring force or internal force that is developed. Okay. So let's take simple example like if we have a rod. So if you apply a force, this is not the ratio force, this is the applied force. Okay. And if the rod gets expanded till here, so the internal force will develop gradually and eventually it will become equals to F, not in the very beginning. So if we plot the graph between the restoring force versus deformation, and let's say the deformation is delta F. So the restoring force will develop gradually. It will become 0 to be 0 and it will develop in the opposite direction. So for a given deformation, for a given deformation, eventually it will reach the minus F. And the work done will be simple as area under the curve. So we know that delta U is minus work done, and work done is area under the curve of F and X
So you can see the x will be how much? So what is the area? Area is minus half into f into delta, because it's negative area. You can see minus f is height and delta. So delta, you can see delta is a positive number. So the work done is easy to find graphically. And why it is a straight line? Because we know that in elastic limit, the stress and strain are proportional, and that's why the relationship is linear. You can see that we have got the answer very easy. It's simply half f into delta. But if you look at the work done by external force, you can see clearly it is f delta, right? Because work is defined as force into displacement. And you can see that the potential energy stored is not equal to the work done by external force. It is only half value. So where the half has gone, so that is exactly the heat produced. So in the process of deformation, the heating is a very common effect that you will see, and it almost 50% of the work goes into heating, and only for 50% gets converted into energy. So delta H is how much? And that is why we didn't use the second definition, because the heat was there and you were not aware of it. So whenever you are not aware of the exact the effect that the external force is producing, always go by the first definition, and then from there you can deduce what is happening. So 50% of the work done by external force is getting stored as potential, and 50% is getting wasted as heat. Anyone having any doubt?
Sir, with that external force, the heating is also.
Yeah, because someone is pulling it, so the rod will not expand quickly, so it will take some time, and in the due process, some heat will also produce. Okay, so this is also a formula that we derive. So what is the other way of deriving the formula? So method, so let's say we make it a general value, say it goes to x value. So if x is the deformation, then we can say that L is the length of rod. So we can write as stress equals to Young's modulus into strain. So this F is restored. So the restoring force is how much? You can see. So restoring force is proportional to x, as I said, it will be. So work done by restoring force is how much? So work done will be minus f dx, because f is opposite integration, and that is why this is exactly equal to the k equivalent into x, the spring formula. If you remember that I told you that spring formula is nothing but the property which comes from the elastic property. So the equivalent of the spring value is ay by L. You can see. And the x will go from 0 to delta L. So the F restoring is equals to minus ay by L into delta L of whole square by 2. Okay. So this looks slightly, oh, this is what.
And basically the formula that we write that at equilibrium we write as F by A equals to, so basically AY delta L by L itself is F. That's why this term is basically minus F delta L by 2. So you can see that why the answer is like this. So you can also derive this. So very basic. So no matter what you choose at equilibrium. So let's write the potential energy part. So potential energy we got as F delta L by 2 or half F delta L. There are many ways of writing, which we'll see. And delta V is the potential energy stored. So we just started as U only. I mean, that's okay. The initial will take as 0. And this we can modify as F by A. This we can write as delta L by L. And this I can multiply with A into A. So it remains same. And now by definition, 1 by 2, F by A is called stress and delta L by L is called strain. And AL is the volume of the rod. And because stress is Young's modulus into strain, so you can also write as strain as Young's stress by Young's modulus. And you can substitute here. So the energy becomes half so energy upon volume is called what? What do you call? Energy per unit volume is called energy density. Because something per unit volume is called density. Right? So we define something called small u, and we call it U upon volume. We call it energy density. So energy density is defined as stress square by 2y. And because stress is a property of a given cross section, therefore it is also a point function. So every point of space with a stress sigma will have the energy density of value sigma square by 2. And that is why this is the formula that we use broadly for finding the energy stored if the stress is known to us. So although we have derived for the rod, but it is true for all type of shape. So every question that we have solved in which the stress was variable, we use this formula only. So how we write is, we write energy density equals to energy per unit volume, and this is sigma of a given cross section upon 2 times Young's modulus. So the energy we write is, and the d volume we can expand further and we can integrate to get the answer. This is how we solve the question actually in general question. Okay. It is clear?
So I want to see the last bit. Yeah, sir, done.
Yeah. So let's take some example to solve. So maybe I can solve one tough question and the rest I will not solve because these things I have done in the work energy power, how to do the work calculation. But anyway, you need to know something basic in the very beginning. But so if you remember that we have done this question in which the rod was their mass in the area, omega, Young's modulus, and everything is given. And let's say I want to know what is the energy stored in this rod by virtue of deformation, and we know the stress is tension upon area, and what was the tension? If you remember, tension was m omega square by 2l, right?
12 into n minus 1.
It was I think l square minus x square, something like this. It was m omega square by l, na? Dimensionally, I can check. You can check the previous notes and tell me just
Yeah,
tell me.
so m omega square by 12 into L square minus X square.
Correct. So this is stress. You can see stress is a variable. So if I go x and cut dx, in this volume I can find the energy. Energy in this volume is easy to find because I know the stress of this volume, sigma, which is a function of x. So energy stored in this volume is how much? Sigma square, which I will never do, into volume. And now in this case, you can write the volume as a dx. That's it. That's the easy way to convert the volume. And sigma here, you have got the answer here. So all the best, you can substitute the sigma as a x function and into the integration to get the total energy stored in the rotating rod. Now this is the challenging problem of the aerodynamic. So the idea is simple. Whenever sigma is a variable, the best way to find the energy is you find the energy density of a given point and do the integration. So with this topic, I mean, we complete the elastic chapter. So rest is only practice. You can do the tutorial and the variety of question that you will solve. And in the tutorial, if you get stuck in something, then you will ask your sir, and eventually, if something goes really wrong, you can ask. So we'll start in the next lecture. New topic called surface tension. Okay. Bye, guys.
Sir,
Yes.
so I want to see the page number 7 and I am doubting.
Same.
So that so delta P into pi r square. I didn't understand that.
For any spherical body, if the force is radial, if force is acting at a right angle to the surface, then net force will be equals to pressure into the projection area, this area, base. That's it. So while teaching some other topic, I will explain why it comes like this. But right now, you can think like this. Or if you want to go in deep, then I need to teach you something more detailed. So it actually goes like this. It's more a mathematical thing. So the net force is going to be along x, right? This is x-axis. So for this half, can I say that net force is going to be towards x only, right?
Yes.
So take a small area here, dA. So the force here acting is how much? dF, correct? And
Yes.
dF is how much? The dF will be pressure into area dA. What is the, if I say this is theta, what is the x component of this force? This
DF.
cos theta. Now what you don't know that the dx cos theta is nothing but the area on the base, the projection of this. So this is 1 by 2 pi r square. 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 This is 1 by 2 pi r s
This area is called dA cos theta. And so if you integrate, you will get the entire base area, full this area. Still, we have not understood. Don't worry, we'll come to this many a times in physics. In different chapter, it will come. So we will keep on coming to this topic. So probably I'll explain the next lecture in surface tension.
Yes, sir. Sir, and in next page, page number 8. Sir, please will you explain the just question again?
Question is we have to find the variation of density of liquid with depth. That's it.
Okay, sir. Yeah, understood.
That is why I have put the heading. Actually, this is a question actually. The question number 13 of SC, but to get that question, this is the theory. And then we have variety of derivation. Something which is difficult. This is very difficult derivation. So just remember this.